or just let me know?
We'll let you know.
Okay.
So hello everyone. Good evening to all of you. And first of all, I would like to thank Nico for agreeing to do this. And SPECTRA 2023 is an astrophotography workshop series and astrophotography competition organized by Nalanda College Astronomical Society. And this is the first installment of the SPECTRA 2023, and Nico Carver from Nebula Photos are here to join conduct this session. And as the president of Nalanda College Astronomical Society, I would like to welcome all of you for the session 1. And in this session, we are gonna Nico's gonna talk about 5 ways to get started in astrophotography. He will be mostly talking about mobile astrophotography and DSLR or mirrorless cameras, using DSLR and mirrorless cameras in astrophotography, because most of us have access to those. So without further ado, I would like to ask Nico to come do his presentation. And also I would like to mention, everyone, please rename yourself as your name and the school. And there will be a Q&A session at the end. So don't ask questions while the presentation is ongoing. You can send them via the WhatsApp group or DM admin in the Zoom meeting. So yeah, I think we can start now.
Thank you, Navide, and thank you so much for inviting me to your group here. It's really exciting to be able to present across the world like this over Zoom. So for anyone that doesn't know me, I'm an astrophotographer who has a YouTube channel. I will tell you a little bit about my backstory today, how I got into astrophotography and sort of where it's led me. But then after giving a little introduction to sort of my story, I will jump into the 5 ways to get started, and hopefully this will give you some inspiration if you haven't started with astrophotography for some easy and practical ways to get started. Like Navide said, I'm going to be focusing mostly on using your mobile phone, or if you have one, DSLR camera with a lens. I'll mention what you can do easily with telescopes, but I know that some of you may have access to telescopes through the society, but that's only going to be just sort of a short part of the presentation. It's mostly going to be more about things you can do with your own devices sort of anywhere. All right, let me share my screen here. Okay. Whoops, sorry. Here we go. So this presentation that you're seeing right now, I've saved as a PDF, and then I also made a resource document, and so both of those are available at this address, tinyurl.com/5waysastro, and I'll share that link again at the end of the presentation. So this is just a way so that if you forget anything I say today, you can always go back to the presentation and look again, and also have clickable links in the resource document to any software or apps that I'm mentioning. So I want to, like I said, just tell you a little bit about how I became interested in all of this. This is me on like an average night today. You can see the binoculars here. I still like viewing the sky, of course, like anyone, but my main event usually now is photographing it. And I often have a couple different setups going. Sometimes, one for more personal projects and one for things that I'm doing on YouTube, like reviewing new gear. But my whole journey into astrophotography started when I was on a vacation to Iceland, which is very high up in terms of latitude. It's something like over 60 degrees. It's almost entering into the Arctic Circle up there. And I went in the winter when the conditions were very cold and very sort of dangerous on the roads, but I wanted to go in winter because it's your best chance to see the aurora borealis. And so I was just really wanting to see these with my eye because I'd always heard about how beautiful they are. And I brought my camera and was amazed at what I saw. I was able to capture them on two different occasions. This was actually the very first night that I was there in Iceland, and I was just driving around looking for the aurora, and out of my window I could see something off on the horizon, and then when I got out of the car I saw that they were actually filling the entire sky with these beautiful displays. So this is a time lapse where you shoot one photo after another and sequence them into a video to show the motion. For anyone that doesn't know what an aurora is, it's really they're really most active on the polar regions, so either the North Pole or the South Pole. But sometimes we get a huge geomagnetic storm, so the sun is very active and exciting all of these particles in our atmosphere, and we can actually see them further south. So we actually just had a huge geomagnetic storm recently on Thursday, and people were seeing them pretty far south, which is pretty interesting. Doesn't happen that often. Maybe every few years they get active enough for that. Here's just another time lapse. This one is at a famous spot called the Jokil Glacier Lagoon. And I don't know if you can see this, but over here on this coast, there's a bunch of other people setting up and photographing them. And I like to say that this was sort of my first experience at a star party meaning an event where a bunch of astronomers get together to view or photograph the stars, because there were people from all over the world photographing them here. And when I got home, I was amazed at, not only the aurora, but the stars, because I'd never really photographed the stars before. And I took one photo out of this time lapse and decided to edit it further. So I brought up the brightness levels in Photoshop and was amazed at all of the colors. I with the naked eye, and even in that time lapse, I wasn't seeing all of these pinks and all of the variety of colors here. So I was definitely amazed at what you can see in processing, and that will be a big theme in astrophotography. What you can see with your eye, or what you can see in a single exposure, is going to be very different than what you can see after you stack many exposures, or even just raise up the brightness levels in a single exposure. Because a lot of information is actually down in the shadows. It's down in the very dark part of the image, where the brightness levels of these dim objects are just above the brightness of the sky itself, which is why light pollution can really mess with astrophotography, because if you have light pollution and the sky becomes too bright, then you'll never be able to reveal some of the dimmest details out there in space, or in this case, in our atmosphere. So when I got home after that vacation, I didn't really do much with astrophotography until I was on other vacations. So this one was actually on a work trip to Las Vegas, but I decided I would check out the Death Valley National Park, which in the US is one of our darkest spots in the entire United States. And so to this day, this is probably the darkest sky I've ever seen. It's in this desert area. And you can see these interesting stones here on the ground. These are another sort of interesting piece of science. They didn't know how these stones were moving. You can see that there's these huge tracks, and so they were obviously moving along the desert floor, but they had no idea how until they set up video cameras and realized that what was happening was the entire playa, that's what they call it, the entire floor of the desert here was once in a while getting covered in a thin layer of ice. And with that thin layer of ice, the stones could actually get on top of it and be blown by even just subtle winds. Just a slight breeze would blow these giant stones along the ice, because this ground is so flat. So it becomes this giant skating rink, and these stones can move. I thought that was really neat. This image was taken with just a DSLR and camera lens on a tripod. There's no tracking or anything like that. What you'll find with this style of astrophotography is if you can get to a dark sky, there's so much to see, even in short exposures, seconds, not minutes. So if you get to a very dark location, it's of course beautiful to see with your eyes, but you can also reveal a lot of color and interesting details with the camera. After that trip, I started researching how to do astrophotography from home, even when you have light pollution. So you can see here on this photo on the left, I was living in a city, and you can see that there's street lights all around me here. It's not a dark location, but there are certain deep sky objects, meaning objects that are outside of our solar system. Most of them are still within our Milky Way galaxy. All these nebulae that we usually capture are inside the Milky Way galaxy, but they're outside of our solar system. And so we often call those deep sky objects. And I found out that deep sky objects can be captured with just a normal DSLR camera and a telephoto lens. This is a little device for tracking, but I found out later you don't even need that to actually capture some of the brightest deep sky objects. So this is the best one, I think, to start with, the Orion Nebula. This is a very easy to find, because of the constellation, and bright deep sky object. The trapezium region, this region in the middle that's sort of coming out as green in this top photo, that region is a stellar nursery where new stars are being born, and it's a very, very bright area of the sky. This trapezium region is a lot brighter than the actual stars all around it. You can see that it gets very easily blown out. But that makes it great for starting out, because it can be very easy to find, and it illuminates some of the nebulosity right around it. So this is just like a very quick test exposure, and you can already see beautiful colors in the nebula just with a stock camera from a very light polluted city. So this is, I think, the best deep sky object to start with. Now, because of our Earth rotating around the sun, we of course have the seasons, but that also means that we have a different view of the sky during different times of the year. And so Orion isn't going to be available at all times of year. For us in the northern hemisphere, it's available in our winter. So from around late October to around now, late March, is the best time to shoot Orion. And in the summer, it will always be below our local horizon, but it would be visible in the southern hemisphere. Okay, and then I very quickly went, what I say is, down the rabbit hole, meaning that I got into telescopes. And when you get into telescopes with astrophotography, the hobby gets a lot more expensive, because at the focal length of a telescope, you need what's called a motorized mount to do astrophotography. Because if you're shooting with a telescope and no motorized mount, the object that you're trying to shoot will way too quickly leave your camera frame. It will, because the Earth is always rotating and you don't have enough time to actually capture it. And trying to just be constantly recentering with a long telescope is very frustrating. So most people need a motorized mount to do astrophotography in that case, and then the whole hobby gets a lot more expensive. But that's not really what I'm going to be talking about today. I just wanted to show you that's sort of where I ended up going. And along that same time, I started a YouTube channel. And so this presentation will be sort of more of an introduction. But if you want a really in-depth tutorial, a lot of my videos on YouTube will be a little bit more in-depth and a little bit more structured with one particular project. So for instance, this one on screen here in the middle, this would be about shooting the Dumbbell Nebula with just a camera and a lens. And I go through the whole process of capturing it and then also using software to process it, so to get to the final photo. There are other kinds of videos, of course, on YouTube, on my YouTube channel, like reviews and things like that too. But the tutorials, I think, are the thing that I'm proudest of. Okay, and then just to finish off my story here, I got so interested in astronomy that I took a job as a librarian. That was my professional background at an observatory, one of the oldest observatories in the world. It's the Harvard Smithsonian Center for Astrophysics is what it's called now, but it used to just be called the Harvard College Observatory. And what I was so interested about working there was that they had the biggest collection of glass plate photographs. And before the digital era, the glass plate was the best technology to capture the sky. They started in the 1880s taking these giant glass plates of every part of the sky. And it was how we learned so much about the universe, all of this classification of the stars and figuring out, our place in the universe happened because we started taking photographs of it. So I was very interested in the history and ways to preserve that, which is why I worked there for a few years. Just this past January, I decided to start working on my YouTube channel full time. So I'm now not working there anymore. All right, enough about me. What I really want to talk about are what I think are the 5 best ways for a beginner with an interest in astrophotography to get started without spending much money, or in some cases, no money at all. And there's plenty of information online about all of these ideas. As I mentioned at the start, I have a resource guide to go with this presentation. I'll show the link again at the end. Okay, the first way that I'm going to talk about here is star trails. And if you have any sort of choice in your first project, I think star trails are the best first project for astrophotography. One, because they are pretty easy. You don't need expensive gear to do it. You can do this kind of project entirely with your smartphone. And I mean entirely. You don't need anything else. There's apps for capture, there's apps for processing. So you can just use your smartphone to capture star trails. And star trails are so interesting because they're the visual evidence of the rotation of our Earth. So if you line up the center of rotation as I have here, what you're looking at in the center there is the celestial pole. What the celestial pole is it's this imaginary line. If you imagine the North Pole or the South Pole and just extend that out into space, that's the celestial pole. So what you're seeing here is the Earth's rotation. That's why that we have these arcs. And if you could imagine these arcs continuing in 24 hours, they would make a complete circle, right? They would, and then the star would be back in the same position that it was the previous night. Now, not quite actually, because we're also rotating around our sun, so the star is moving a little bit, but pretty close, right? Because the main motion of the sky is the Earth's rotation. That's the fast motion of the sky that makes it so that you look up 1 hour and then you look up another hour and the constellation is in a completely different spot. That's because the Earth is rotating so quickly around its own axis. All right. So the other thing that I think is great about Star Trails as an astrophotography project is it's an excellent way to start exploring the color of the universe. Because when we look up at the night sky, usually we don't see any color, but that is just because of the nature of our eyes. Our night vision is not very good. If you compare it, we actually know that other animals on Earth have better night vision because they're nocturnal. But our night vision is pretty monochromatic. We can, if we let our eyes adjust, we can see things in the dark, but it's very hard for us to see much color. The colors that we can see tend to be more the greenish colors, so it's easier to see green at night because we have more green cones. There are some stars that are so bright and colorful that we can make out their color, especially through binoculars or a telescope. But with just the naked eye, you might just be able to barely see that, oh yeah, that star is a little bit redder, that star is a little bit bluer, but you can't see much color. But when you take a photograph, and especially when you take a star trails photograph, what a star trail does is it spreads out the light from a star across many pixels. And when you do that, all of the brilliant colors of the stars becomes apparent. And so I think this is another way to sort of also get interested in the science of stellar classification. And this is something that we've been studying for over 100 years. And it ties into the life cycle of stars. So I think it's really interesting to take a photograph and then start exploring what all of these colors means. So over here, I have a diagram showing the life cycle of what we call main sequence stars. And you can see that the very bright hot stars are these brilliant blue, and then most stars in the Milky Way galaxy are going to be white and yellow because they're in the middle part of their life cycle. Our star is sort of a white star. Of course, it looks very yellow or orange when we look at it from Earth, but that mostly has to do with how our atmosphere refracts the light. If you actually get out into space, our star looks pretty white. Okay. So, in terms of how to make a Star Trails image, I have videos on this on YouTube for both Android and iPhone, so you can check those out. But I wanted to put up this slide showing you the apps that I recommend. If you're doing this on Android, you can really just get this one $2 app, and I think everything else is free. There might even be a free option for the intervalometer, but this is the one that I found works best. So basically what this does is it uses your normal camera app, but instead of you having to tap the shutter button on your phone over and over again, the intervalometer automates that process. So it's pressing the shutter button over and over again. And you might think, oh, well, why would I need that? I'm not lazy. Well, the thing is, it's pressing the shutter button yourself with your finger is always going to sort of disturb the phone a little bit. And you want the phone to stay very still through the whole process of capturing it. So this app is useful for that. After you've taken all of the photos, you need an app that will stack them all together to make the trails. And so there's a free app called Star Trails that does just that. You just load in all of the photos and it stacks them all together to get your final image of the star trails. And then you can bring that finally into a program like Snapseed to edit it, to change the saturation, to bring out those colors, or change the contrast if you're in a light polluted area and you want to make the image darker, things like that. The last app here, Stellarium Mobile, the reason I mention that is it's useful when you're out taking star trails photos to learn the sky a little bit. And well, it can also tell you which direction is north. I mean, you could use the compass app on your phone, but this one's a little bit more fun because it shows you all of the constellations. So you can sort of look up at the constellations, then look at your phone and understand which way to point. And then there's similar apps on iPhone as well. Okay, the next style of astrophotography that I want to talk about is called afocal astrophotography. And this also uses your mobile phone, but it's taking your mobile phone and attaching it to the eyepiece of binoculars or a telescope. And it's easiest to do this if you have a little adapter. These adapters range in price from like $10 and up. But what that adapter does is it allows you to really clamp your phone right onto the eyepiece so you don't have to try to hold it. These are both single exposures, so you can capture both deep sky objects. And remember, deep sky objects are ones outside of our solar system, and solar system objects, things like the moon, the planets, the sun. You can do both of those with afocal astrophotography. The moon and the planets are probably the best way to get started with solar system objects and the best way to get started with afocal astrophotography in general. The sun is also possible, but you will need a filter for your telescope if you do that. This image here I took with a very inexpensive telescope. This is called the Celestron First Scope. It's only $65, though one of the ways they got the price down is the telescope tube is not metal. It's a thick cardboard. And there's probably ways to make a telescope like this yourself, or there are ways. You just would need to grind a mirror and find a cardboard tube to put it in and some way to focus the light. But this is pretty inexpensive in terms of a telescope. This is called a tabletop Dobsonian telescope design. And then the actual optics are arranged in what's called a Newtonian reflector, named after Isaac Newton, who was the inventor of this kind of telescope. Basically, what it does is the light comes down the front of the tube, it reflects off a primary mirror down here at the bottom, and then reflects back up to a secondary mirror, and then out the focuser. So the light is reflected into a secondary mirror that's at an angle and then focused up here. The focal plane is up here at the top. It's a good kind of telescope in that you can capture a lot of light because you can make the aperture a lot bigger with mirrors. So it's a very good kind of telescope for viewing the sky. Better in some ways than a refractor, which is going to be more limited by how big you can make the glass elements. Well, mirrors you can make a lot bigger. Anyways, this was taken by just putting the phone right on the eyepiece and using my camera app to take a 1 second single exposure. Now, to get this kind of color, you need dark skies, but you don't need anything like special in terms of the equipment. This was just taken with one of the very basic Plossl eyepieces that came with the telescope. And then I think that the moon is it's even more possible to get a very sharp image with this method with the moon because it's so bright. So I took this with a type of telescope that's very popular, at least here in the US, which is a Mac Cassegrain. It's a little, again, a small telescope, but it again uses mirrors to reflect the light into the eyepiece. And this thing that you're seeing here is that telescope smartphone adapter. This one I think is by Carson, but there a lot of different people make them, and again they range in price. So this one I think is a little bit more expensive, like $50, but you can get them for $10. And they do make it a lot handier to attach your phone to an eyepiece, because if you're just holding it, it's a little bit harder to get it in exactly the right spot, and also hold it steady enough to get the picture. Okay, I'm going to spend a little, quite a bit more time now on this method. This is the method that I've had the most success with on my YouTube channel, because I think that it was something that was known about, but not a lot of people were doing yet, and it can really give you great results. It's a little bit more expensive than the first two methods I mentioned, but if you know someone who has a DSLR and a telephoto lens and a tripod, it's really worth doing, because you can capture pretty much any of what are called the Messier objects, these deep sky objects that were found by Charles Messier in the 19th century from Paris. And because he was shooting from Paris, even back then, there was already light pollution. They're all northern hemisphere objects, but they're all super bright. What Messier was trying to do was find comets. And whenever he found something that wasn't a comet, he added it to his list. And this became basically the first catalog of deep sky objects. Okay, so for this method, you don't need the newest cameras. You know, newer cameras will have lower noise, but even digital cameras that were made over 10 years ago, like this Canon 60D, are low noise enough that this method will work just fine. What's more important is the lens, and the ideal lens for this kind of method is a telephoto lens, meaning one that has more than 50 millimeters or up focal length, because you can do this, of course, with a wide angle lens, but it just means the deep sky object will be very small. And so if you zoom in like this, you won't get all of this detail if you're using a very wide angle lens. So I think, 50 millimeters and up is a good target. And the faster the lens, the better. So what that means is if you look at the f number of a lens, if it says f8, that means it's a slower lens. It's a fraction, so that means 1/8 of the total area is open. If it says f2, that means 1/2, so it means half of the total area is actually open. And so the faster you can make that lens opening, meaning the wider it is, the brighter your picture will be, and the more successful you're going to be with this kind of method. The other big thing with this method, like all of these, is if you can escape light pollution, you're going to be a lot more successful. So if you can find a place, even, just 5 minutes outside of the city, you're going to be more successful than if you try to do this right in the middle of the city, right? So any gain you can make with reducing light pollution is going to be worth it. Okay, I wanted to show you this because with this method, we're going to do something a little bit different. With the other methods that I showed you, we weren't using stacking in this way. With this method, what you're actually going to want to do is take multiple pictures of the same thing. And that doesn't make a lot of intuitive sense when you first think about it, but what it allows you to do is actually take the equivalent of a longer exposure. And the way that it works is because photons of light are arriving randomly from these distant objects, there's a lot of uncertainty. There's a lot of noise, is what we call it, associated with it. There's also noise from the camera. And so through calibration of the camera noise and stacking, which improves the shot noise, we can really dramatically improve what we see in one of these pictures. And so in this picture, this is just a 1 second picture, and you can see it's dominated by noise. Both the camera noise is showing up as these streaks of color, these streaks of green and magenta. That is camera noise. The shot noise, or the noise from the uncertain nature of photons arriving at the camera, is the broken up, grainy nature of the shot. And there's so much shot and camera noise in this picture that you can really only make out the center of the galaxy. The rest of the galaxy is there, but it's lost in the noise. It's lost in that grainy noise that we're seeing. Now, if you take all of those images and you use calibration frames to try to handle the camera noise a little bit, these are your dark frames, which means just a picture taken in the dark with the lens cap on, and flat frames, which are trying to get rid of dust and things like that. If you take these calibration frames, you use them, and you stack your, this is 1,000 pictures of the same thing together, it really reduces the noise. And you can see, compared to that last one, which looked very grainy, this one looks very smooth, right? And you can now see not only the center of the galaxy, which we could see in that first 1 second shot here, but you can see that the galaxy extends out quite a bit. The Andromeda galaxy is our closest galactic neighbor, and it's actually the full width of it here, like this, across, is actually 6 full moons across. So it's really giant in the sky. But the core is very bright, while these outer parts, the full extent of it, is quite dim. So we need something like stacking to bring that out. And then even this picture is not processed, it's just stacked. So all I've done here is take the 1,000 short 1 second pictures and stack them together. After processing, we can get to a picture like this. And compared to this picture, this one looks more noisy, right? So there's always a trade-off. If you want to bring out the dimmest details, you might have to accept that by bringing those out, you're also going to raise the noise levels. So it's always sort of, that's part of the fun of processing. It's a creative process. It's deciding for yourself, well, how much am I going to try to change this image to bring out these dimmest details when I know they are associated with the noise floor. Some of the things that you're doing in processing, other than bringing out the details, are changing the color balance, because we know the sort of the true nature of Andromeda. So we know that the center is full of these yellow and white stars, while the more that you get out to the edges, you get more blue hot stars. And so we can correct the color balance to account for that. We can also change the saturation, because normally when you get back and astrophotograph and do this stacking process, you might not see a lot of color, but if you increase the saturation, that color that's actually in the photo can come out. And then lastly, we can change the contrast, and that just means how dark are the darkest parts of the image and how bright are the brightest parts of the image. So a very low contrast photo looks more like this, where the entire image is sort of gray. And one of the main things that we do in processing an astrophotograph is to change that process. That means to change that contrast. Okay, and another thing that I love about this style of deep sky astrophotography is that it's very possible to do with entirely free software. This software that I'm showing here, Siril, SIRIL, is at siril.org, and it works on any kind of computer. So I'm just going to exit my PowerPoint here for a second and show you this software. Just because I want to show you how quickly you can edit a astrophoto. One second, I'm finding it here. Okay, so this is my stacked Andromeda picture. And this is another thing that I think is a little bit confusing for people new to astrophotography. After you stack your pictures, it can look like this. And you might think that something has gone wrong because the picture is completely dark. What this picture is actually showing is the raw photo in what we call linear mode, a linear space. And a linear space means that there's been no transformation of the pixels applied. So all of the data is in here, but it's all compressed down into the shadows. And so normally when you take a picture with your phone and you see that JPEG, a transformation has already been applied where certain pixels are multiplied more than others. And I know that's sort of confusing to think about, but it's how digital photography has always worked. It's just that much of it has been hidden from us. So in astrophotography, though, we want to do this stretching, this transformation of the pixel data ourselves. And so, but before we do that, there's actually some processes that we can work on while the data is still in this linear state. However, it's much easier to do those processes if we can see what we're working on. So what astronomy software does is it allows you to apply a preview of what the image will look like without actually making the transformation yet. So if you look down here in Siril in the middle where it says linear, if you click on that, you can change it to one of these other previews. And so I'm going to change it to the auto stretch preview. And you can see just like that, we now get a more visible representation of the actual data here. So we can now see Andromeda Galaxy, but we now see that there's also an issue with our data. This is very, very common. What this issue is that the color channels are not scaled in the same way. So if we look at the red color channel, we can see that it's much brighter than the green and the blue, with the red color channel being brightest, the blue being somewhere in between, and the green color channel being the darkest. You'll often see the exact opposite. You'll see the green color channel being the brightest. It doesn't matter which one it is. What we care about is that we want to fix this issue, right? We want to make the image look more natural by scaling the color channels in the same way. So if we think of a histogram, all of their histogram bumps would start at the same point in the graph. And so there are ways to do this in any program. The way to do it in Siril is quite easy. We go up to the image processing menu, you go down to color calibration and choose color calibration. And you define what's called a preview where you have the background. So you don't want to define this box on your galaxy or on too many stars. You want to find a place that's just basically sky. So I'm just going to click and drag, and I've now made this preview box right here. And then here, I'm going to click this button that says Use Current Selection. And then it takes all of the pixel data in that box and averages it together to determine this is the background level. So then if I click background neutralization, look at that. It largely fixed that unnatural color of the background. I'll just show you before, and then here's after. Okay, we also can try to fix what's called the white balance of the scene. So this is the highlights. And right here, you see it says white reference. You can try to manually fix the white balance by just changing the scaling factors of the red, green, and blue channels, or you can do it the same way we did the background reference, where I can take something that is bright in the scene. So I'm going to take the nucleus of the galaxy here and make a rectangle around it, and then click Use Current Selection and click Apply. And you can see it changed the nature of the colors. I'm going to close this now, but I'll just show you a before and after here. So here's before, and you can see the galaxy looks too green. And then here's after I fixed the white balance. And you can see now we have much more neutral, natural colors. Okay, now with enough work, we could use this entire frame, but just because this is going to be a short tutorial today and I don't want to spend too much time working on it, I'm going to crop down just to the galaxy and get rid of a lot of this color shift that we're getting all around here. A lot of this color shift has to do with the nature of untracked astrophotography. Because you're taking many shots and the galaxy is constantly moving in those shots, you'll get the most data in the middle, and out towards the edges, you're going to get less data. So there's going to be a lot more color noise. Okay, so I'm going to crop. To crop in Serial, you just click and drag out a box like this, and then right click and choose crop. Okay, so now we're nice and close in on the galaxy. It's looking pretty good already. But remember, this is not stretched yet. If I switch back to the linear mode, this is what the image actually looks like right now. This auto stretch is just a preview. So to actually stretch the image, you can use all kinds of different tools here. The classic one is this one called histogram transformation. It looks like this. It's pretty easy to use. You just can either apply the auto stretch or you can use these sliders here to change it. But Serial has a new one that I'm really happy with. It's called this generalized hyperbolic stretch. So I'm going to use this. I'm going to start with the data linear. And for this first stretch, I'm just going to turn up the intensity all the way to 15. And I'm going to bring this stretch factor over until I start seeing the stars. And this is a really fun process, I think, is the process of stretching. You can see the image come alive through each stretch. So I'm going to apply that. And then I'm going to just do the same thing again. Okay, and I want you to look at this, what's actually happening here. This is called the histogram. And so when you start out with linear data, this is the before and this is the after. You can see that the data is bunched up over here in the shadows. And what you're trying to do with stretching, the reason we call it stretching, is you can see this is all of the data and it gets stretched out. This histogram represents all of the different brightness values in the picture. So the stars and the core of the galaxy are way over here. There's not many pixels that are actually this bright. This, which we call the histogram bump or the histogram peak, represents the sky. And in astrophotography, you generally want this sky to be off of the left edge, but you don't want it to be way over here, like halfway. If I continue to stretch this, you can see if I put that histogram peak halfway, the whole image gets blown out because the sky shouldn't be this bright, right? You want it darker. So even if you're in a light polluted place, you have a lot of control over how the image ends up looking through this stretching. Okay, and if I stretch it like that, I'm going to apply this. And now I want the image to look darker. I can actually change the type of stretch here to this bottom one, linear stretch, and then in parentheses it says BP shift. BP stands for black point. And what this does is it doesn't actually stretch out this histogram bump, it just moves it to the left, right? So if I just take this slider and I move it to the right, you can see this histogram bump moves to the left, closer to this left edge, which would be pure black. And so that way we can darken the sky. So doing a combination of these two things, the generalized hyperbolic stretch like this, apply, and then the black point shift allows you to get a very nice looking photo with plenty of color in the stars, but also the right level for the sky. So you can see this is a good level for the sky where it's not completely black, but it's dark. It's not blown out. And this histogram that you're seeing here is about what you want to see for astrophotography. The peak can be way over here or down towards the shadows, but you want it spread out. You want to see other pixels here.
I'm sorry to interrupt, but I think we can't see the windows that are popping up on serial because you're only sharing the serial window.
Oh,
if you
thank
can,
you.
Please
Yes, I'll
reshare the
change
screen.
that. Sorry about that.
Yeah, sure.
Let's see.
Yeah, now we can
Okay.
see that.
You can see it now? Okay. Sorry about that. So I was talking about this this stretching, and sorry, I missed a lot of with the histogram. Let me go back here a few steps. Okay, I'm going to open that back up. Sorry. Here we go. Okay, so this is what I was trying to show. There's these two types of stretches you can use in this window: the generalized hyperbolic transform and this linear stretch. And the way that I usually use them is I use this one first, this generalized hyperbolic transform. And the way to start with this one is just turn up the stretch intensity all the way to 15. And then use this stretch factor so that you start seeing the stars over here. And with all of this kind of stretching, you can do it in passes, meaning you don't have to do it all at once. You can apply this and it resets the whole window, and then you can do it again. Okay, so now we're seeing this. This is the histogram peak or histogram bump. And with astrophotography, you don't want to bring it all the way out here, because you can see when this histogram peak is in the middle of the histogram from this is the shadow end, this is the highlights end. When the histogram peak is right along the 50% line, this is what your image would look like. The sky would be blown out, and you don't have nearly enough contrast to see the difference between the sky and the deep sky object. So what you're going for in astrophotography is something closer to this, where the histogram peak is out from this left edge, but not all the way out here in the middle. And another thing that you can do is you can move this whole histogram peak to the left. So this, the generalized hyperbolic stretch, is good for spreading out the pixels. So literally stretching out the histogram so you get more midtones and more highlights. But when you want to just darken the sky, you can go to the linear stretch or the black point shift. And when you do that, the whole histogram peak can move over to the left towards the shadow area. Now, what you want to be careful when you're using this, the black point shift, is don't do that. Okay, you see what's happening there where I've moved the whole histogram to the exact left edge? Now, you might think that, oh, I want that. That looks good because the sky is now truly dark. It's truly black. But the problem with doing this is you are now what's called clipping data. So some of these pixels in the actual galaxy are now clipped to black, and you can never recover them. If you apply this transformation right now, the only way to get that data back would be to undo. You can't do this and then hope to bring out the galaxy later. So while you're processing, you want to make sure that you always leave a little gap here from the left edge to the start of the histogram. When you're all done with processing, a final step could be to take this black point and move it right up against the left edge till the sky is as dark as you want. But while you're processing, you always want to leave a little gap there. Okay, another interesting thing you can do with this I'm not going to touch on this too much, is this idea of a symmetry point. So I can define an area here. So I can say I want to work on this outer part of the galaxy and make a box. Hit this little eyedropper here. It sets that as the symmetry point. And then when I stretch, the point at which this curve is bending is this point. So the actual like symmetry of the curve is defined by this point that I've put out here on the image. So this is a really powerful stretch. You don't have to use it right away. You could just use a more basic one, but I think that this is well worth learning. I'm still learning it myself. It's fairly new to Cyril and new in astrophotography in general. But I think it's very powerful, which is why I wanted to show it today. Okay, so this is sort of what I would call a good initial stretch of your data. And it's a fairly honest representation of what you've captured. Now, if you want to push it further, there's certain things you can do. One of them being you can apply a saturation boost. So let's just see what happens if I really up the saturation. You can see one of the issues with color saturation boost is the stars get very colorful. It's harder to bring out the color in the galaxy. So one thing that we often do in processing is take out the stars so we can remove, so that we can process just the deep sky object on its own, and then we can add the stars back in. Now, this new version of Cyril has made that really interesting and easy because we can put this star removal process right into the program. It used to be that you had to leave the program, do the star removal, and then come back in. Now you can actually do the star removal right here in Cyril. So it's called StarNet. It does require a separate download and installation, but it's once you get it working, it works very well. I'm just going to do it here. Okay, and this is also something that they've added in the newest version of Cyril. What this is the image looks the same here as it did before, basically, but now we actually have two images composited together. And This one is what they call the background, meaning both the background and the galaxy. And this one is just the stars. And so the benefit here is now if I define an area, I'm going to do right here in the galaxy, I'll set that as my symmetry point. And I start stretching the image. I'm just gonna go back and forth here just to show you what I mean. This is only stretching the background and the galaxy. The stars, you can see, are staying the exact same. And that's because we actually have removed them here and added them back in, and they're sort of on their own layer, so to speak. So this set of sliders is for messing around with the stars, and this set of sliders is just for changing the brightness of the galaxy in the background. So this is a very powerful technique. You can see you can bring out a lot of detail in the galaxy this way without making the stars completely blown out. So I'm going to do something like that. And now you can see all of these beautiful dust lanes in the galaxy and really get the spiral nature of it. And I can change the black point here with this slider. You can just leave the stars alone. That's probably what I would do here. But I want to show you, if you click on this advanced button, if your stars felt too big, you can actually shrink them right here. You can change the stretch mode to inverse generalized hyperbolic. And then when you raise the stretch factor, it actually makes the stars smaller. You can see that. Now, if I just keep going with this, eventually you can see the stars disappear completely. So this can be useful too, in that you could be applying some transformations over here and just be focusing on the galaxy and take the stars out, and then slowly add them back in by just moving this stretch factor until they look right. So here's completely in, but if I want to dim them a little bit, if I want to make them a little bit smaller, I can do this. And again, this is with this inverse generalized hyperbolic transform. Okay, they have separate apply buttons, so I'm going to apply both of them. Okay, and now with the stars a little bit smaller and the galaxy a little bit more prominent, I'm going to try that saturation again. Okay, and I think that looks a lot more successful because the stars aren't so big. But I'm seeing one small issue, which is the center of the galaxy has a lot of green noise. So I'm going to use the remove green noise command. And just like that, only with Cyril, you can see we have a beautiful image of Andromeda. And this was done completely with a DSLR, no tracker. And so hopefully that little processing demonstration showed you it's not super difficult. The tools that we have available today are really amazing for making a beautiful astrophotography image. Okay, I'm going to switch back to my PowerPoint here. And I just wanted to show you Andromeda is one galaxy, but I mean, one example of something you can shoot untracked, but there's actually lots of things in the sky and in different seasons. So Andromeda is mostly a late summer and autumn object, but the Milky Way core is a great one to do in the late spring and summer. This region is one of my favorites in the upper right. This is the Cygnus constellation. You also have the Pleiades star cluster, which is a nice bright reflection nebula. So there's lots of things that you can shoot without a star tracker and just a DSLR and lens. Another option, or there's two. Okay, so the last two are going to be options that you can do just on your computer without even, uh, going out under the night sky. Of course, I always encourage you to try going out under the night sky, but if you want to be more like a professional astronomer, they actually use what are called remote telescopes, and the remote telescopes can be in the darkest places on Earth. So, for instance, this micro observatory is, you can see, in the desert, but a remote telescope can also be out in space, like the James Webb Space Telescope or the Hubble Space Telescope or Chandra or any number of other uh, space telescopes. Now, one of the limitations on Earth is our own atmosphere. So, a big motivation for putting a telescope out in space is it's much easier to observe in other wavelengths of light, like X-ray, infrared, all of these things that the atmosphere and all of our noise down here can sort of interfere with. This project is run by my former colleagues at the Center for Astrophysics. It is a project to allow you to control these robotic telescopes. They're always adding new things here, so you can now search for exoplanets using these too. But the one that I tried was just, again, shooting my favorite thing, which is nebulae. So I decided I wanted to shoot the Ring Nebula, which is this bright, but pretty small planetary nebula. A planetary nebula is just when a star is dying and it's sort of at the end of its life cycle, it can outgas all of its elements, so, hydrogen and oxygen and all these things into these beautiful nebulae. And so that the Ring Nebula is a good example of that. So you can imagine that there was a star here, and there actually still is a little white dwarf, a remnant of a star in the middle. But this is all of the star's gases after it's sort of unraveling, after it's starting to blow apart. Another kind of stellar death is called a supernova remnant, and those can get a lot bigger because they're explosions in the sky. So if a star gets so big that it can't handle itself and then it explodes, that's a supernova remnant. Well, this one is a more sort of a quiet death, a planetary nebula. So this is showing how you can use this micro observatory. You can pick one of the objects to observe. You get to decide the exposure time and the filters you want to use. And so what this is trying to do is sort of, in a simplified way, show how professional astronomers use these robotic telescopes and get to pick an observing plan, like, what they want to observe, how they're going to take the pictures, what filters they want to use. And then you can process it right here on the website. This is all possible without leaving the website. So you can take the red, green, and blue images and composite them together into a full color image, which is what I did here with the Ring Nebula. And you can see some really interesting things about it. You can see that the center, which is dominated by oxygen, is this nice green teal color. And then as we get out to the edge, where we get the ring, you get more of the hydrogen and get a different color. So it's a lot of fun to try out this micro observatory. You don't have to buy any equipment. All you need is a connection to the internet. And then a little bit more complicated, but just as possible with the internet, is you can download very high quality data from the Space Telescope programs. So I processed both of these images using data that I downloaded from websites. This one on the left is a very unusual galaxy called Zwicky 18. And then this one on the right is you might have seen, you've probably seen, is from the JWST, one of the first images that new space telescope took. And there is a portal for downloading data. there's also what's called the Hubble Legacy Archive, which might be a little bit easier to use than this. But I do have a video up on finding the JWST data through this website. So you can check that out to try to find things that you can actually process on here. And when you download the data from any of the space telescopes, it's going to be black and white data, because what all the space telescopes do is they use a monochromatic camera, a mono camera, which only shoots in brightness levels. It just from 0, which would be completely dark, to something like 65,000. So there's all these different levels of brightness that it can record. And then to target different wavelengths, they put different filters in front of the camera. So the James Webb Space Telescope is an infrared telescope, meaning that the wavelengths that they're targeting are outside of our human vision. They're much redder than we can see. But what we get back are these black and white images, and then you can combine those in interesting ways to visualize color. It's not true color in any sense, but it's an interesting exercise to visualize color by combining different filters. The Hubble Space Telescope actually has true color filters on board as well. So, for instance, when I showed that this galaxy earlier, this was actually taken with color filters that are within our normal human vision, while this one, if you want to tell someone what this is, you have to represent it as false color, because it's not the true color that we can see. It's infrared data mapped down to our color range. So there's a lot of interesting science you can get into by downloading data and playing around with it. And there's lots of people online who have just started this way and made interesting actual careers out of this. If you start really getting into it, there's a lot that you can learn and a lot that you can sort of get involved with. All right, I'm going to stop there and open it up for questions. But I wanted to mention again this website address, this tinyurl.com/5waysastro will bring you to a Google Drive folder with two things: this presentation as a PDF and this Google Doc with links. So, I have video how-tos for all the different methods that I've mentioned today, and also links for any apps, including that Cyril that I did the long demonstration of. All right, thank you very much.
Navide, are you there?
Yeah, thank you, Nico. So for the Q&A sessions, you can send the questions to one of our admins, and we will direct that to Nico. And Nico, we have received some questions. So the first one is, can we see some of your astrophotos? So he's asking to see some of your work.
Yes, I'll pull that up here. Okay, so my website is nebulaphotos.com. I haven't updated this too often, but it represents some of my best work. The thing that I'm interested in shooting personally is these large clouds of dust and gas. So, for instance, this one is a section of what's called the Heart Nebula. And you can see that these structures of dust can make really, really beautiful things to photograph. You can really zoom in and see all of these interesting details as they get blown by stellar winds and are formed by the whole life cycle of the stars. This, stars being born and stars dying, and you get these really interesting structures in nebulae. And then I also like this kind of thing because this is a Hubble palette narrowband. So that's sort of what I was talking about with the JWST, where you're taking data from very specific filters shot in black and white and mapping it into color, and you can then have a lot of creativity with how you map that color. But I'm also interested in trying to get to more true color representations of nebulae. So this is a more true color where the red emission are all of these the hydrogen alpha, and the blue emission is represented by the O3 data. So this is a giant supernova remnant in Cygnus. This sort of football-shaped or egg-shaped blue part here in the middle is an ancient supernova explosion where a star exploded. We don't know where the center is anymore, but it has all the telltale signs of a supernova remnant. So they're pretty sure that this is what's left over after a star millions and millions of years ago exploded. Show a couple others.
Yeah, so thank you, Nico. And we have another question from Disat. He's asking, what cameras would you recommend for astrophotography?
I am an advocate for Canon DSLRs. They're the most common brand of DSLRs ever produced, so you'll find more of them used. And then also, because Canon was popular for all of astrophotography, there's a lot of accessories built for them. There's a lot of lenses you can adapt to them. So I just think Canon DSLRs are probably the easiest way to get into DSLR kind of astrophotography. In terms of phones, any kind of phone, smartphone can work, but of course they've been getting better and better. So I think the newer Samsung phones, some of the new Sony and Huawei phones have had huge advances in the camera technology. But this one that I bought a number of years ago, this is the Huawei P30 Pro. I've always been impressed by the camera system on this one.
Okay, so there's another question asking, is there any time period for taking clear pictures?
Time what?
Time periods.
Oh, time periods. Yeah, so time periods for taking clear pictures. I think
I think
there
meant like spring or spring, autumn, winter wise, I think.
Yeah, so I think that the different seasons offer different kinds of deep sky objects, and right now we're leaving the period where you have what are called the winter nebulae, like the Orion constellation, and entering a short period called galaxy season, where in the northern hemisphere we're pointed away from the Milky Way. So you're seeing out into basically the universe, but away from the core of our Milky Way galaxy, so that you can see all these different galaxies. But it's not a great time for shooting in the methods that I talked about today, because the methods that I talked about today are better when we're more pointed towards the core of the Milky Way. But the good thing is galaxy season is pretty short, and even by May, if you stay up late at night, you can see the Milky Way core area, where there's a lot more going on and a lot more that you can shoot with more wide angle lenses and cell phones. So I think the best time in the northern hemisphere is sort of summer through winter, and spring what we're in right now is sort of the worst time.
Okay, so there's another question from Ginura. He's asking, can you tell more about how you visualize colors for the black and white colors while preserving scientifically accurate data to be used by observators and scientists? And also he's asking if it's possible to use those photos in scientific research.
Most of the photos that I take wouldn't be used in scientific research. The reason is because most images that they want to use for scientific research, they're thinking about what they want to capture before they take the pictures, right? So it's rare for them to want to seek out pictures that are just they don't know exactly how they were made and how I process them. And then I usually don't process them with science in mind. But to answer your question a little bit more fully, one way in which amateurs are sort of interacting with scientists, or actually I'll mention two ways. One is amateurs make discoveries all the time. And this is something I think that a lot of people don't realize, is that how many discoveries amateurs make. There's a team led by Marcel Dreschler, who's discovered like over 100 planetary nebulae in just the past few years. And many of those are followed up by scientific missions. So it doesn't actually matter what their photographs were. They just were the discoverer, and then they pass that information about where the object is onto a science team. And what the science team does to actually do real science with it and confirm the discovery is they use photometry. So photometry is where you use very specialized filters to study the true color of the object. Most amateurs don't do photometry because it doesn't make beautiful pictures. What it does is it breaks apart the spectrum into a rainbow, so you can actually understand about the color. But most of us don't have the gear to do that. But if you did want to get into it, there are some resources for amateurs to get into photometry. You basically need a little prism to break apart the colors, so you can actually understand where the emission lines are and different things like that. But one way in which amateurs really do help the science is by being the first people to discover something and then passing that information on to a science team.
Okay, so there's another question asking, is there any free apps to take time-lapse videos?
Yes. Well, let me think. Time-lapse video. I guess I only know about it well, a lot of phones have a time-lapse feature built into the actual camera app. So I guess the first thing I would do is make sure that you don't have that already built in. But another way to do it with star trails, at least, is to use those apps that I mentioned. So using an intervalometer app to take many pictures in a row and then stacking those all together. You can also, of course, take all of the pictures that you took and bring them onto your computer. And on the computer, I definitely know of some free apps to do time lapse. On Windows, there's a free application called Virtual Dub, virtual and then DUB, and that's a really easy to use one for making time lapses. I showed it in a recent video about 3 different ways to do night sky photography.
Yeah, thank you. So there's another question asking, what is easier to capture, galaxies or nebulas?
I would say nebulas mostly. The one exception is sort of Andromeda, which I showed today. The problem with galaxies is, other than Andromeda in the northern hemisphere and the Magellanic Clouds in the southern hemisphere, most galaxies are very small. So to capture them well, you need a larger telescope. And but many nebulae are quite big. So I would say in general, nebulas are easier to capture than galaxies.
Okay, so there's another question by Ramiro. He's asking, what are best for astrophotography, mirrorless cameras or DSLR cameras?
So the best pro mirrorless cameras, there are some that are made specifically for astrophotography. So right here I have the Canon EOS RA. So this one was designed with astrophotography in mind, meaning that it's been what's called the IR cut filter inside the camera lets in more of those red nebulae. Now you can take any DSLR or mirrorless camera and modify it to do the same thing. So you don't need to buy this one. You can take any pro camera and modify it. There are instructions online to do that yourself, but sometimes there's also professionals that will do it for you. In terms of just DSLR or mirrorless cameras in general, I wouldn't necessarily go for the ones with the highest megapixel count. Instead, the best cameras for astrophotography are the ones that have the lowest read noise. So this is going to get a little bit technical, but let me just share my screen here for a second. Okay, so I'm going to go to this website is called photons2photos.net, and there's a very good chart on this website called input referred read noise chart. And you can compare any set of cameras with this. And so, for instance, if I take my Canon RA, I'll just do the Canon R here, and I compare that to a much older camera. I'll compare it to the Canon 200D. You can see the much older camera is still holding up pretty well, but let me put in another one. Okay. So this green line is representing the Canon 20D. This black line is the Canon 200D, and this blue line is the Canon RA. And what you're looking for in a camera that is good for astrophotography is the one that has the lowest read noise. So if you hover over these little dots, you can see it measures the read noise in electrons. And so at ISO 1600, we have 2.3 electrons of noise. If I look at this camera up here, this one has 3.5 electrons of noise. So, quite a bit more. So the lower you can get this read noise, the better the camera will be for astrophotography. And I would say that's a much more important thing to look at for deep sky astrophotography than something like the megapixel count or just how expensive a camera is or anything like that. This is probably the most important thing.
Yeah, thank you. So we'll talk about like two questions and stop the Q&A sessions because the time is running out. So there's a question asking what is a cheap but performing tracking mount we can use to photograph the night sky when starting out?
So what is achieved by the tracking mount?
He's asking what is a cheap but performing mount or tracker
cheap. Okay.
we can use to photograph.
Oh, sure. So I have one right here. Okay, so really cheap, but good for wide angle lenses is like a barn door tracker. So if you have like some wood and screws, you can make a tracker where you actually just manually move it, and it's not accurate enough for telephoto lenses, but for a wide angle lens, if you're just shooting the Milky Way, It's fun, and you can learn about trackers a lot this way by making your own. For about $30 in parts, you can make a barn door tracker. Going up from there, this is called the Move Shoot Move tracker, and I think it's about $200 US. But it's motorized, and so it'll be more accurate. And so this is probably the cheapest but pretty good performer is the Move Shoot Move. Then up from there, you get to something like a Skywatcher Star Adventurer, which I think is about $400. So yeah, that gives you sort of a range. A barn door tracker made out of wood, maybe that you have to move yourself, is $30. This one's about $200, and then a Star Adventurer is about $400. If you can afford the Star Adventurer, it's going to give you the best results because it has a counterweight system, so you can balance it, and so you can use longer lenses on it and get more accurate results that way.
Yeah, so with that, I think we can stop the Q&A session. And thank you, Nico, for answering some of our questions. And if you have any questions, we will send you the link of his Discord server, the Nebula Photos Discord server. You can ask any questions there from the public section. I think so. I think today's event was a success, and I like to thank you, Nico, for coming here on such notice. And I would like to ask Ramiru to come and thank everyone for participating. David.
Good evening, everyone. I'm very honored to vote of thanks on behalf of the Nalanda College Astronomical Society on this occasion. First of all, I'd like to offer my heartfelt thanks to Mr. Nico Carver for conducting this event and sharing your knowledge and experience with us. And also, I'd like to make you all who have participated a kind request to follow and share the Nalanda College Astronomical Society and Nico Carver on social media. Then you will be able to be notified about new things related to this field. And also, I'd like to thank our masters in charge, Mrs. Surani Nagoda and Mrs. Vijini Herath, and the committee members and alumni members of Nalanda College Astronomical Society for advising and helping us to make this event more success. I make this an opportunity to thank you all who have participated today in this event. And also, I think that you have gathered a lot of knowledge and astrophotography from this session today. As a volunteering society which has knowledge and experience throughout Sri Lanka, this is the only pleasure we have got from this event. At last but not least, I'd like to thank again to Nico Carver for sharing your knowledge with us and to all who have effort to make this event success, at least within a word. Hope to see you at the session 2 of SPECTRA 23 Astrophotography webinar series with such a mesmerizing experience. Thank you. May the blessings of Mother Nalanda.
Thank you, Ramiru. And before we end the session, so I would like to ask everyone to turn on their camera to take a photo of reminding us this memory of SPECTRA 2023 session 1. So if you may please turn on your camera.